Welcome back to Physics 142. We've been talking about magnetic fields, and specifically we've been focusing on the effects of magnetic fields. So we've been thinking about, if you have a magnetic field, what sort of force do you experience? And we wrote down that the force from a magnetic field ends up depending on the amount of charge and how that charge is moving, the motions of the charge. And interestingly, we noted that it's a cross product. We have to take V cross B, that the force, magnetic force, is perpendicular to magnetic fields. This is in contrast with forces from electric fields, right? Forces from electric fields just depend on the amount of charge, and they go along the electric field lines. Force is in the direction of the electric field. So magnetism, the effect is sort of this perpendicular force. With electricity, the effect is along magnetic field lines. So in this video, though, I want to sort of shift a little bit from thinking about what's the effect of a magnetic field on the motions of a particle, what sort of forces do you experience from the magnetic field, to thinking about how do we create magnetic fields. We know from electricity that if you have some sort of point charge, maybe it's a positive charge, that creates electric fields, right? That you use charges to create electric fields. And the formula that we had for that is that the electric field created by some little amount of charge dq, right, ends up being, if you add up all of the charges dq and you go some distance away from that dq and you square the distance away, right? So if I'm interested in the electric field at some spot here, I need to think about how much charge I have, how far away I am from that charge, right? So how much charge I have, we call that dq, how far away I am, that's r squared. And then there was this constant k, this electric constant, and if we have a bunch of charges, or some sort of continuous charge distribution, right, then we need to add up all of those charges, and that's how we found the electric field. We also noted we'd put in a unit vector, r hat, to indicate that the electric field is in this radial direction, goes away from the charge, right? We also, one other way that we had of writing that is this constant k. We could write that as 1 over 4 pi epsilon naught. That's another way we wrote the constant, and we still have dq over r squared, all right? And so this said, for some amount of charge, or for some charge distribution, we were able to figure out how much electric field was created by that charge. So the question is, how do you make a magnetic field, and what sort of formula do we use to compute how much magnetic field gets created? Well, just like with magnetic fields, we realized magnetic fields only apply a force if your particle is moving, right? If the velocity of the particle is non-zero. Similarly, it takes moving charges to create a magnetic field. And so what's a moving charge? Well, moving charges, that's sort of like current, right? So if we think of, if I have some wire, right, and I could think of a little piece of current in that wire, right, that, so let's take a little piece of that wire, we'll say that has a length dl, and there's an amount of current I flowing through that, right? And so dl is normally represented as a vector, right? So we could draw that with a little arrow here. So this is a little piece of current flowing through this wire here. And so current is moving charge, and so if we have a little bit of moving charge, we expect that should be able to create a magnetic field. And so the goal here is to write a formula for this. This is something that scientists in the early 1800s were working hard on, trying to figure out if you have a little bit of moving charge, how much magnetic field does it create? And they were able to come up with a formula. Some of the first people to come up with it were a couple of scientists named Biot and Savart, and so this is called the Biot-Savart law. And basically what Biot and Savart figured out is that if you take your little bit of current, just like you take a little bit of charge, all right? So I'll write my little bit of current as IDL, all right? That as you go further and further away from the wire, all right, you take spots further and further away from the wire, the amount of magnetic field, like electric fields, also drops off as the distance you are away squared, all right? So right, like dq over r squared ends up being IDL over r squared. There's a different constant in front. We need a magnetic constant rather than this electric constant. And so the constant that for magnetic fields is always written mu naught over 4 pi. All right, so the magnetic constant is this mu naught. So let's just quick write that down. Mu naught is the magnetic constant. All right, that's what it's called. And mu naught has a value, just like K had a value. The value of mu naught, interestingly, ends up being 4 pi times 10 to the minus 7 Tesla meters per ampere. All right, and it's sort of interesting that it ends up being exactly 4 pi times 10 to the minus 7. That's why this 4 pi is often included in this formula. And this ends up having to do with how these units are defined. But for now, let's just take this to be the value of this constant. All right, so we have a constant, we have an amount of current, but we're not quite done yet because there's this issue with magnetic fields that magnetic fields, they don't just go radially away from the charge like electric fields, right? There always is this sort of perpendicular nature to it. And so we have to have a way of incorporating that perpendicular nature. And so the way that that gets incorporated is that we like to think about, if this is our position that we care about, maybe we call that point P, all right? The vector that takes us from our little bit of charge to point P, that's usually, we call that r, right? That's that distance r, and it has a direction to it. And r, the r vector, right? The r vector has two parts to it. It has a magnitude, so I could call that just r, and it has a direction, which we could represent with the unit vector r hat, right? So it has the magnitude and the direction. And it works out that this r squared here, this is just the magnitude, just depends how far away you are. But the direction actually gets incorporated in an interesting way. And the direction of the magnetic field around a wire always ends up actually wrapping around the wire. And so we'll think about this more in some sort of future example, but the way the formula works out is we take the direction that the current is moving, all right, the direction of this dl, and we end up taking the cross product with the direction of the r vector with the r hat unit vector, all right, so we do dl cross r hat. So what that says is that at this spot P, the magnetic field that's created by this IDL is, if you want to figure out the direction that that magnetic field is going, you would take your finger and point it along DL, and then you'd curl your other fingers in the direction of the R vector, that R hat direction, and my thumb would point into the whiteboard here, would be pointing down. So that says that the magnetic field that's created right here at point P is into the page, all right? So in my drawing here, we end up getting, I didn't leave enough room. I'll make a little label right here. This is into the page, all right? And you can tell that from this cross product. Now, r hat, the unit vector, only has magnitude 1. So in terms of calculating the amount of magnetic field, this is just a 1. All right, so you can ignore it for calculating the amount, but it's really important for getting the direction of that magnetic field. Now, the last thing for the Biot-Savart law is, of course, dl is just one little piece of current, but really all the little pieces of current along this wire are creating some magnetic field at this spot P, and so you need to add up all of the contributing magnetic fields, right? All these different r hat vectors, right? You need to add up all of these, so they should all point at point P, right? All of them are going to contribute at point P, and that's an integral, right? So we need to integrate along our entire wire, and that's how you get amount of magnetic field B. So this is the Biot-Savart law, all right? This one right here, all right? And this is the equivalent here of essentially what we called was the Coulomb's law, right? Very similar to that for creating electric fields, where we had dq over r squared, and you had to add up all the dq's, right? K times q over r squared, that gave you electric field. Here it's going to be amount of current over r squared, and rather than k, our constant is mu naught over 4 pi, and we have this little extra trick that takes into account the direction. So we'll want to do some examples of this, and so I will do those in, I'll do a bunch of examples in future videos.